Good morning, class. I know that we're just a little bit late on getting this lecture done, but I've been having a little trouble with technology arriving and getting set up. So we'll go from here. Now, a few things I want to set in place before we have this lecture on climate change. The first thing that I want to say is, if you have any political problems with this topic on one side or the other, I want you to set them aside. For the purposes of this class, we are going to accept that climate change, man-made climate change, is real, and we're going to accept the science as it exists, and then we're going to work within that scope on how do we handle the environmental economics of it. So by accepting that as a fact, we then need to understand a little bit about what the climate change effects are. Now, the best way to get that information is to go to the source, and the source is a combination of NASA and IPCC. Just a few facts so that you have an idea of what we're talking about. Number one, in the last 100 years, the sea has risen on the average 8 inches. In the last 130 or 140 years, the temperature of the Earth has increased by 1.9 degrees Fahrenheit. The ice sheets have been losing 478 gigatons per year in recent years, and carbon dioxide is up 419 parts per million. Now, to understand what that means that we've gone from about 250 parts per million to about 680 parts per million of carbon dioxide. So if we assume that man has a portion of this influence, and we can see from the graphs from NASA that there is a cycle to both global temperatures and also carbon dioxide, and that we're at the peak of that cycle right now, or what appears to be the peak of that cycle. We then have to think about what it is that would be the most efficient in terms of dealing with it. The news reports, if you listen to them, only talk about one potential solution, and that's mitigation. So mitigation would be stopping the production of greenhouse gases, mainly carbon dioxide, and or reducing it dramatically. And that would help mitigate the problem. Now, one of the challenges we face there is that the climate change or warming process is a positive feedback loop. What that means is that as the temperature rises, it causes the sea to warm, and as the sea warms, it releases more carbon dioxide. That new carbon dioxide then causes additional warming, which causes the sea to warm, which releases more carbon dioxide, and so forth, because the sea is the source of most carbon dioxide. That positive feedback loop is in place, and scientists expect it to continue even if we were to abate on the mitigating greenhouse gases that we're producing now. The rise in temperatures and sea level would still continue pretty much at the same rate for the next 100 years. What we might be doing today could affect the sea levels and temperatures 100 years from now. So we're looking at what can we do today that might make a difference 100 years from now. Why is that important? Because when we're calculating the cost-benefit analysis, the benefits are going to come 100 years from now. What is it now that we're spending in terms of future costs versus the present cost? To understand the implications of the future value of the present value of this situation requires that we recognize that the $3 trillion we would spend today has a much greater value in the future. So what does this mean? Using our future value formula, we can calculate the value of that $3 trillion using an interest rate of 5% and for 100 years. We end up with $394.5 trillion in future value. This is the equivalent of 4.5 times the global world economy. So we have to think very carefully about the impact of money we spend today when we don't get the value until 100 years from now. So mitigation is what we're hearing the most in news, but there are other options, and we need to discuss them. So a second option would be engineering. Now, engineering means that we wouldn't try to abate the production of the greenhouse gases, but instead we would put money and resources behind the development of some process for removing the greenhouse gases from the upper atmosphere. Some of this has already been done with the creation of some sulfur compounds that can be seeded and will bond with the carbon dioxide and will bring it, because it's heavier, drop it out of the atmosphere, and it's non-dangerous. In fact, it is a form of fertilizer, so it would help the plants as a result of being dropped on them. Now, there are some concerns about this approach because we've never done anything like this before, and we might be additionally messing with nature and could cause other problems that were unforeseen. Nevertheless, engineering is an option, and a fairly inexpensive one relative to the others, and we would see immediate results rather than 100 years from now. Of course, the third option is adaptation. This is discussed at the NASA website, but we never hear about it in the news because all they ever talk about is mitigation. And the debate between the two sides being there is no climate change or we need to mitigate. But in this class, we're going to discuss the three different options and what makes sense. So with engineering, the idea is to try to remove the offending items from the atmosphere. With adaptation, it is to accept that the changes are coming and adapt slowly over the next 100 years, which we're going to have to do anyway, to the changes. So as the ocean rises, we would have to perhaps build walls like we've done in New Orleans. As the temperatures rise in some areas, we may have to abandon those areas in terms of farming, but the higher temperatures in other areas would open them up for farming. And again, this is something that NASA discusses and recognizes on their website. I'll put up some quotes on the screen for you to look at and read from the NASA website so you can get a better feel for this. So the question is, do we mitigate, do we engineer, or do we adapt, or some combination of those? And this is a particular case where we have to think about those things. Now, what are the predictions for the future? So NASA is claiming that in conjunction with IPCC, that the potential rise in the oceans is somewhere between 1 foot and 4 feet. And there's a 95% probability that it will be somewhere in that range. So this sounds a little bit like what you've been doing with your variables in the Monte Carlo simulation. We don't know where it's going to be, somewhere between those two numbers. And if it's 1 foot, that's not much of a difference. But if it's 4 feet, it could make a significant difference. Again, we only have a probability that it's somewhere in between those two numbers. As far as temperature rise is concerned, again, the range that they're giving us is something in the range of 1 to 3 degrees Celsius, or 1 to 4 degrees Fahrenheit approximately. What would that do? Well, it'll have a big impact in some areas in a negative way, and it will have a big impact in a positive way on others. What is the net? Well, that's part of what we have to think about, is what is the cost, the net cost, the cost and benefit of that. We're not going to be able to do that in this class, but what we can do in this class is discuss it, how we might go about doing it, and this is something that will help you prepare for the homework assignment that you have for your next case study. So what are the impacts of climate change? Well, there are the impacts on physical and biological systems. There are the impact on natural systems, such as the rainforests, the coral reefs, etc. There's the impact on countries' economies. Now, this is an interesting situation because the areas that are going to be most negatively hit by climate change are those areas that are nearest the equator. And what's interesting is that actually very few people live near the equator. I didn't realize that myself until I got on a globe and started looking, but you have some people in Ecuador, in that area in South America, and you have some islands, and you have part of Africa that's impacted, but that's it. And so as a percentage of the world population, it's something like 0.5% or less of the world population lives along the equator. So these are people that are going to be potentially the most impacted. So what does that mean? Adaptation, whether or not we implement the mitigation processes, is going to require us to probably relocate many of the people that live in those locations. Why? Because temperatures are going to rise to the point where they can't maintain crops, and the oceans are going to rise, in some cases covering the islands where people live. So we have to think about those developing or undeveloped areas that need to be able to be fixed. As far as adaptation is already happening. Temperature rising, people are moving to different areas. One of the things we're seeing is longer cycles for growth of crops, which of course is a positive thing. We're able to grow more crops each year for the world and feed more people, so that's a positive thing. So how do we go about addressing this from a mitigation standpoint? Well, this is a very difficult problem, because that requires us to get the cooperation of all the nations. And we are, of course, a developed nation, and some of the countries are developing nations like China and other countries. And of course, then we have the undeveloped nations as well. Now, if you're a developing nation like China, mitigation is not an appealing approach, because they're in the process of building up their economies. And as a process of building up the economies, that means that they have a lot of production of greenhouse gases, more than, say, a developed nation like ourselves. So we're asking China to basically take a step back economically, and they don't want to do that. And so we have a prisoner's dilemma. So I'm going to bring up the prisoner's dilemma for climate change on the video, and we will discuss that. In this particular game scenario, the player 1 and player 2, let's assume that player 1 is the US and player 2 is China. Now, if we have a choice of abate or pollute, abate, of course, would be a form of mitigation, as we would abate of our pollution. And the numbers here would represent some kind of a payoff. Let's assume that these are close to trillions of dollars or billions of dollars of value. And so what we have is a situation in which player 1 can abate and would save $5 billion, and player 2 can abate and save $5 billion. However, if player 1 abates and player 2 chooses to pollute, then player 2 is ahead by 7 instead of 5, and so would prefer that choice. On the other hand, if player 2 chooses to abate and player 1 chooses to pollute, then player 1 would receive a benefit of 7 rather than 5. And so we have a prisoner's dilemma because it is in the best interest of both parties to pollute. And so the result is the pollution continues and the mitigation does not take place. Thus the prisoner's dilemma. The solution that we have discussed in class is the implementation of an assurance game in which the players are promised a second game during which time there will be punishment or a reward depending on what they do in the first two cases. And so what we have is a situation in which the US, for example, could propose trade restrictions on China if they don't abate. Of course, that could end up in a trade war and be worse for both countries. Or, of course, they could always consider, a nuclear option or something like that. Of course, that's ridiculous. The case here, though, is that what we expect is that this will not be resolved and that mitigation is an unlikely scenario to resolve the situation. So let's talk real quickly about how this is going to work with the online videos. First, I will be doing a series of these to help you prepare for your writing assignments, and I will also be doing a special video to help you step by step to go through your Monte Carlo simulations. So what I'll do is I've got to figure out how to do screen videos so I can capture the videos on my screen. But once I've done that, I can then put them up and show you step by step exactly what you need to think about. I'm not going to show you exactly how to do the Monte Carlo, but I will show you cell by cell some of the things that you need to know from a high level in putting this together. The second thing I want to mention is that this week, in addition to climate change, I will be doing a lecture on recycling of e-waste. That's not really covered very well in the book, but it's something that I have a lot of personal experience with. When I was at the Technology Association of America, Tech America, I was responsible for putting together the education and training courses for the large corporations who produce electronics on how to handle their e-waste. And so I would put on these lectures and training classes for people like Google and Apple. They would send their personnel there to be trained. I didn't actually do the training, but I put this all together. And of course I had to sit and listen to this, so I'm aware of many of the problems and issues that come up. So we will have that discussion as well. What I think we need to do is to think about the three different choices here and apply then our structure of thinking for policy on top of this. So the structure of our policy for this particular kind of problem would be, number one, what is the economic problem here? And of course, we need to use our terminology to evaluate this. But in this particular case, it is negative externalities being produced by firms and individuals and others who are producing these greenhouse gases, imposing a cost on others in the process. So we have a massive negative externality problem. The second part then of applying our process to this is to consider the four different approaches and what combination of them might be best for addressing this problem. So number one, we have regulations. Well, regulations are a good, potentially good approach for, say, firms in the US, where we could use the same approach we talked about for stationary pollution, where we potentially could designate how much of the greenhouse gases can be created, put into the atmosphere, and get that under control. But how are we going to apply that to China? How are we going to apply that to India? How are we going to apply that to other developing nations? These countries don't want to participate in that change, and it's going to cost them tremendously. We can't force them to do it unless we threaten a nuclear bomb. Or maybe not. Maybe there's something through game theory we can learn. but I want you to think about that based on what we discussed in game theory. Next piece of this to consider is Pigouvian taxes and subsidies. Again, we have a problem because we can't force countries to pay a tax or a subsidy or receive a subsidy. So we're not going to be able to use that unless we can solve the international problem of anarchy, because you see, the world government is anarchy. We don't have a world government. We have a whole bunch of different governments with no world government. And so we have, basically on the global scale, we have anarchy. So that's not going to work. And then, of course, the third approach is well-defined property rights. But again, that's not something we can solve because we don't control the property rights or the enforcement of property rights globally. And finally, we have social norms. Now, social norms is something that we can use by putting pressure on other nations through film, through television, through promoting and advertising the potential damage. So this is a very, very difficult problem to solve. And your case study this week is going to be very similar. Now, I didn't give you this particular problem for your case study, but instead I gave you the case of the bluefin tuna. The bluefin tuna is a large fish. They're not as large as the yellow tuna, another tuna, but still a large fish. And the market for one of these fish is about $100,000. So if you catch one of these large bluefin tuna, you can sell it for approximately $100,000. So there's a lot of motivation for people to catch these fish. And as a result, they have seriously harmed the population of the bluefin tuna. So the problem is the bluefin tuna moves in schools all over the Pacific Ocean, from country to country. So how do you apply property rights there? How do you address the different issues associated with the bluefin tuna? It's the same problem as climate change. And so I'm giving you the climate change problem, but I'm giving it to you in a little bit smaller dose by having you consider the bluefin tuna. So what I want you to do then is take what we've learned from climate change and apply it to that case study and see if you can come up with the best approach to addressing it. Again, this may be a situation in which you use technology to track the bluefin tuna, or maybe to create property rights of the bluefin tuna. You have to think about the game theory implications between countries. How do you control that and get them to be good citizens of the world, so to speak? Anyway, in the next lecture, we'll be talking about recycling, and prior to that time, we'll have our video on your Monte Carlo simulation. Thank you.